Okay, I'm Richard Walton from the University of Warwick, and I'm going to be moderating this first session before lunch. I'd like to thank CBMM for organising this event. As usual, it's exceptionally well set up and planned, I know, in a long time in advance, and it's a privilege to be part of the conference once again. It's a privilege also to be introducing a session on solid state chemistry. I'm a solid state chemist myself, so it's an honour to be introducing some of the distinguished practitioners in this field, who are also, of course, acknowledged global experts in battery materials. So as Ricardo's just told us, the first lecture is going to be given by Professor Stanley Whittingham, who was awarded the 2019 Nobel Prize for Chemistry, a share in the Nobel Prize for Chemistry for his work in the development of lithium-ion batteries. Stanley's originally from the UK, studying chemistry at the University of Oxford, where he was also awarded his DPhil degree. But he's worked in the US for a good many years, firstly in industry, and then at Binghamton University, where he's currently a distinguished professor of chemistry and materials science. So I'll hand over to Stanley now to give his Charles Hatchett Award lecture, which is entitled, "What is the role of niobium in nickel-rich layered oxide cathodes for lithium-ion batteries?"
Thank you very much for that introduction. It's an honor to give this presentation, and I notice we're here in Cambridge, but your first two speakers are both Oxford graduates. So I've known Clare for many, many years. She and I were running an EFRC in the States for about 10 years. So what I want to do is really talk about some of our work on niobium, on these high nickel NMC materials, and really point out the role of niobium and how important it is to modify these materials. But first, I need to really thank these folks up here, the US Department of Energy, who supported this research for almost 30 years now, continuously. And I want to point out the comments the Nobel Committee made that the three of us laid the foundation for a fossil-free society. The foundation is there, but all of us now have to work together to actually use the batteries, use the systems, and clean up the environment. I just want to make the point here, and don't worry about all the numbers on this slide, just look in the red box and you'll see what we get out of a commercial battery today, and it doesn't matter whether it's a little one or a huge one, is less than 25% of theoretical capacity, theoretical energy density, whether that's volumetric or gravimetric. So there's still huge opportunities to improve that, and really that's what we're doing. And we have a major consortium in the United States called the Battery 500 Consortium. It's about 4 national labs, 6 universities to do this goal of improving things, and our goal is to get to 500 watt-hours per kilogram from today's 250. The major challenges are we've got to get more lithium into our cathode, which means that will also reduce the cost. We've got to really get rid of the graphite anode. You need 72 grams of carbon to store 7 grams of lithium, and the carbon takes up 50% of the volume of the cell. So that has to go. And we need fundamental science to actually make our cathode materials better conductors, both for ions and electrons. Then we can make these cathode materials thicker. So this is the goal of our Battery 500 Consortium, is to increase that energy density, and we're making good progress there. Again, don't worry about all the details at the bottom, but all you need to look at is really the scale here. Our first 5 years, we got about 50 cycles out at 300 watt-hours per kilogram. Now in 2022, we're about 800 cycles, now at 350 watt-hours per kilogram. We have got data at 400, but these days anything above 350 is export controlled, so we can't talk about it until after we've published it. So it's got to be in writing, then we can discuss it, but we are making progress, and I should say all our work has eliminated the carbon anode. We're using pure lithium metal, and we've also changed the electrolyte. So these are the typical cells we make now. We use pouch cells, and these are all made by Jay Xiao, who is an ex-PhD student of mine who works at Pacific Northwest National Lab. So all these numbers are what we say are real numbers. We weigh the cell, measure its volume, and then with the electrochemistry. So I have to point out to those of you not in the battery business that 90% of what you read in the public literature is hype. Don't believe it unless somebody else has already tested out the systems. So what we're trying to do is get it even higher. And to get even higher, what it means with these layered oxides, we've got to go to higher and higher higher and higher nickel contents. So what we want to do is push the nickel as high as we can. At the same time, we want to lower the cobalt as much as we can. The cobalt's the most expensive element. There's child labor issues there in the Congo. And right now, China dominates the cobalt. Essentially, all the cobalt goes through China to be processed. There's little processing in the rest of the world, with a few exceptions. So there's now a cobalt mine in Idaho, the United States. That material gets processed in Brazil or in Finland, not in the United States, not in Canada. So some of these materials from the mine to the finished product travel about 50,000 miles. That's not sustainable long term. So what our goal is to increase the nickel content. So we want to go along this axis here. Higher nickel gives us higher capacity, but at the same time, what that does is reduce the stability of these materials. So all these layered oxides are thermodynamically metastable when we charge them. So those metals in the +4 oxidation state, they want to release oxygen, and they will spontaneously release it at these temperatures here. And they'll release it at lower temperatures given the right catalyst. So there's safety issues as we increase the nickel content. So the highest nickel is about 200, 220 degrees centigrade when it will release that oxygen. If we want to make it safer, then this lower nickel content, lower energy density. So we're trying to push over here. We want to get the safety and infinite lifetime. So our batteries hopefully are never going to operate at those temperatures, but that temperature is a direct measure of how reactive these materials are with the other cell components, particularly the electrolyte. And I've just plotted the same sort of data here, some of our data. The only parameter that matters for this evolution of oxygen is the nickel content. That the degree you charge it to or anything else you put in there doesn't have much effect. So it's totally the nickel content. So we need to be aware of that as we push forward. So how do we reduce the reactivity? There's several ways. One is to reduce the surface area. So if we have one big single crystal, it's going to be very little surface area. It's going to be not reactive, but you're not going to get much power out of it. So there's clearly a trade-off. But I'll show you in a moment, there's a big push now to go to single crystals. A second way now is to actually modify the material to reduce its reactivity, and that's where niobium comes in. I'll talk about that. And another way is to substitute in the bulk of the material and reduce the mobility of the oxygen ions so they can't be evolved. And this will, if we do this, we should get higher energy density. And I'll talk about this first cycle loss in just a moment. Now, single crystals. What we're going to be doing is really going full circle if we do that. Here is Exxon 1976 single crystals. These we measured millimeters on the side, and if we wanted, we can make these centimeters. But the commercial batteries all were millimeters on the side. Sony, for their lithium cobalt oxide, would try to make their particles as large as they could for safety reasons. Again, they want to reduce the reactivity. But then as we got into higher power devices, then folks wanted more surface area, so get a higher current out of it, and that's where these meatballs came in. So these are about 200 nanometer primary particles. These secondary particles are about 10 microns across. So these work very well, but they're obviously very reactive. So you can get a lot of power out, but it means if things go wrong, you can get a lot of bad things happening too. So there's been a push for the last 3 or 4 years, and I think initiated mostly by Jeff Dahn. Let's go back to the beginning, go back to single crystals. So we reduce the surface area and reduce the reactivity. The other thing it also prevents, you see here, all our primary particles are jammed up against one another. These particles expand and contract about 10% on cycling. So these meatballs tend to crack. If you have single crystals, then they're not connected to each other. They can freely expand and you shouldn't get cracking. And cracking is what gives us capacity fade. And again, my ex-student Jay has shown that if you have these single crystals, keep them 2 to 5 microns in size, they themselves do not crack as you expand and contract them. So this is really where a lot of the effort is going now. And the real question we have now is how can we easily make single crystals in tonnage quantities? Because I should emphasize all these NMC materials are today made by batch processes. So single ceramic pots, fire them up, and off it goes, not continuous. If we've got a good manufacturing, folks in the audience can come up with a continuous process that would cut the costs a lot. So let's look at the first problem we can address, and that's what we call the first cycle loss. All these materials, when we charge them, so here's the charging curve, charge it up to here, charge up to, we've gone up to about 4.6 volts, commercially they're about 4.3, and this is 80% nickel, 10% cobalt, 10% manganese. We discharge down the same curve, you never get all the lithium back in again at room temperature. This is what we call this first cycle loss, and this is what we've been trying to solve. So what we found out, this is a diffusion control process. It's not clear yet whether it's in the bulk of the materials or in the surface of the materials. But if you look at the solid circles here, this is the diffusion coefficient, lithium going in, and you can see this falls off the cliff at about 80% lithium content. So this is a vacancy diffusion mechanism, and in fact you need 2 vacancies next to each other for the lithium ions to diffuse. So it gets more and more difficult as you fill the lithium up. And you can look in this audience. The easiest way is to look at a conference room. If somebody comes in now, there's probably an empty seat somewhere in the middle. So everybody has to move to let that person in. It's the same issue with these cells. Taking the lithium out, there's no problem. So this, like emptying electrolyte, it will all flow out. So fast charging is feasible with these materials, but we can't get this in. If this is really kinetic controlled, and if we raise the temperature, then it should get better. But first, let me just show you what happens as we change the charging voltage. Increase the charging voltage, we take more of the lithium out. So this is 4.2 all the way to 4.8. And we put this one in here to show you that we're now getting a separation of the charge and discharge cycles. And this is because at 4.8 volts, the system is unstable and the electrode materials is reacting with the electrolyte forming resistive materials on the surface. There's a little bit of it here. So what we've done here is charge them up, discharge it to 2.8 volts, then hold this for about 4 hours so you can see more lithium gets in if we just hold it there. Again, indicative of kinetic control. So if we now raise the temperature from about 21 to 45, you can see here, this gap here is much smaller than in this case, same here. So again, indication of kinetic control. Now you see at 4.6 volts that we're getting separation. So at 45 degrees, we've got more reaction going on with the surface. So this is always a problem with these materials, the compatibility with the surface of the material and the electrolyte. So we have clues that we should be able to solve this. Lithium cobalt oxide itself does not have this first cycle loss. So what we did was a study, and we'll compare 811 with cobalt oxide. The black here is room temperature. This case, we've now only charged up partway 120, and discharge it. If we hold it now for 100 hours, we get all lithium back in at 45 degrees, much faster. Clearly kinetic control. And lithium cobalt oxide, there's no issue. There's no loss there. So clearly we should be able to get our material and try to make it behave more like the pure lithium cobalt oxide. And that's what we've been doing. And we've been modifying it by using niobium. We chose niobium because lithium niobium oxides are good ionic conductors. So if we put a film of niobium oxide on the surface, the lithium ion should still be able to get through that film. Unlike a standard method of, say, putting aluminum coating on where you've got aluminum oxide and it will increase the resistance. So what we've done is modified our material both by coating and by substitution. We've introduced the niobium in two ways, initially taking our meatballs and soaking them in a niobium solution and firing them up at a temperature. And depending on the treatment temperature, at low treatment temperatures, we get a surface coating. At high temperatures, the niobium goes totally within the lattice. And what we found out, surface coating gives us a higher initial discharge capacity, but the bulk coating gives us better capacity retention. So what we did is, say, put the niobium in there. We added niobium in two ways, either with no lithium in it or with some lithium in the solution. If we don't have lithium in the solution, then with these very high nickel contents, 80%, we all have lithium carbonate or lithium hydroxide on the surface. But the niobium in there, it removes that lithium, forming our lithium niobium oxide films. So what effect does this have? So if we do low temperature, 500 degrees centigrade, here's our original meatball. You can now see we've got a coating on the outside and the niobium diffuses into the top few layers. But what we found out by doing a joint X-ray neutron study is it's much more complicated than that. The surface coating is in fact a mixed niobium manganese phase. So the niobium goes in the first few layers, kicks out the manganese that goes into that surface coating. So we've now got this mixed phase, and this mixed phase does indeed reduce this first cycle loss by about between 40 and 50%. Okay. So it clearly works. We can get some of this effect with aluminum, but it's not as much. And you notice here we only need 1%, whether it's 1, 2, or 3% makes no difference. So just a trace of niobium in the surface will reduce that first cycle loss. What our second thing to do was when we discussed this with our sponsors, DOE, they said, you've taken the meatballs. They've been fired once, you're now going to put niobium on them and you're going to fire it again. That's an expensive second step. So what we then did was made our own layered oxides. We got the precursor, which is the hydroxide. With the hydroxide, you then fire it up with, say, lithium carbonate or lithium hydroxide. We added a niobium at that stage. So we didn't add the extra step. And we got essentially perfect material all the way from 0 to 2%. At the highest niobium contents, you can see we're now getting some surface species of this complex niobium oxide, but at lower niobium contents, we don't see that. So in this case, the niobium's now gone totally within the lattice, so we've now got a substituting material, and this is the extra phase we see. We see this lattice is expanding a little bit, which proves that the niobium is in fact going in there. So what effect does the niobium have? Mostly positive, but not all positive. So here we have our capacity. So you now see our capacity is holding pretty well, but this is the one with the highest capacity. This is about 0.7 niobium in it. As we put more and more niobium in this case, we're losing initial capacity, but we're maintaining the capacity. So here's the niobium free. It loses capacity continuously. So clearly niobium is stabilizing the lattice. And I just show you the same data here as a percentage. So you can see with this purple one, there's essentially no loss in capacity at all for this 200 cycles. So it totally stabilizes the lattice. So it's doing very positive things. We don't like the idea that it's dropping the overall capacity. And I should point out this is now with 90% niobium. So we're trying to push the 90% nickel. So we're trying to push the nickel content as high as we can. And we're staying in a reasonable potential limits for the stability of the electrolyte. So here's the data for these 4 different 0 niobium to 2% niobium. And you can see here's the capacity fade continuously occurs from the beginning to the 200 cycle, a little bit less with 0.7 niobium. And by the time we get to 2% and even at 1%, you can see now there's no capacity loss at all. So this niobium is really stabilizing that lattice, which means that niobium in our mind is stopping that diffusion of the oxygen, so the oxygen cannot be evolved at the surface, so you can't form these so-called rock salt phases at the surface. There's no question that niobium is helping. And you see that same way if we do these electrochemical plots. Here, this is dQ by dV, so it's capacity versus with the voltage. And you see with no niobium, this shift of these redox peaks is continuous cycle to cycle. By the time we got to 2%, these stay exactly on top of each other all the way from the 10th to the 200 cycle. So clear again, stabilizing the lattice. And the reason it's stabilizing lattice, it's stopping the formation of these resistive films on the surface. So the black here is the pure material. Here's the one with 2%. So you can see in cycle 50 here, here's the black one. Resistance has increased, much less on this one. Now here's the 150th, 200 cycle, always increasing for the niobium-free material. The resistance is much, much lower for the niobium-treated material. So we've eliminated, for practical purposes, that resistive layer on the surface. So what is it really doing? So we introduced the Niobium-lithiating stage. We found that it lowers the capacity, but what it is really doing is it's preventing those meatballs from cracking. So you can see here's a typical niobium-free material. You get these large cracks after 200 cycles. Add the niobium, you can see you got some minor cracks between the particles, but none of these large cracks. These large cracks allows electrolyte penetration, which then forms resistive films on the surface, which is causing that increase in resistance and loss of capacity. So here is a similar plot I showed you before. Say the capacity we would hope to be up here, but it's down here. It's exactly flat for 3 different cells. So we can reproduce this data that niobium is stabilizing these materials. So it's making these materials viable. And this just got published a few months ago since your last meeting in Asia. But what we did, and I should say, let's go back to this one from there. This is a standard electrolyte formulation. We've got lithium metal. We've got the standard commercial carbonate-based electrolyte with LiPF6 in it. We've switched over to what we call our improved electrolyte. This is the one developed by Pacific Northwest National Lab. They went back I won't say quite 50 years, but almost 50 years, and said, let's go back to the ethers, which is what Exxon used. Ethers plate out lithium much better than carbonates do. And you can see now, here is 1.4% niobium, and here we're getting over 200 milliamp hours per gram, and no capacity loss for 300 cycles. And here's the Coulombic efficiency. So clearly, the niobium is stabilizing this material. The ether electrolytes are letting us make better lithium metal. So we're getting the reversibility on that side as well. So a few concluding remarks. By controlling the processing conditions, we can put the niobium on the surface, or we can substitute the full lattice. And the niobium actually modifies the electrochemical behavior, stops these surface films being formed, it stops the impedance growth on cycling. We know we can form coatings on the NMC. It's a complex composition, but it does reduce the first cycle loss. What we're now doing, having made the substituted materials, we're now going to see if we put a coating on that substituted material, whether that will give us additional benefits. We see some loss of capacity when we substitute it, but it's not obvious we're seeing that with ethers. What we do need is cost-effective manufacturing technologies. The methods we're using today are not cost-effective. And I want to just finish up by making a few comments. We got the niobium folks here. They're, I think, in what we call a friendly country. So the big issue we have in North America right now, same issue we have in Europe. We do not have a regional supply chain, and we have to build a regional supply chain. That's both for the raw materials coming in and for making the batteries, using them, and the rest of it. So right now, the US government is, I think, about 5 years behind the European community in investing in the battery business, but they've invested several $billion starting right now at Binghamton. We're going to build what we call a mini BIC that you have in Warwick. We've got $110 million from the federal government and the state to build a pilot facility. But more importantly, what we have is over $12 million to build up a workforce training program, because the big issue in North America, there's really no one who knows how to manufacture batteries. We no longer train power electronics engineers. It's not, can I say, sexy enough for academia to study. So those folks don't get trained, so we're going to change that. And the other thing, in our local region, IBM was formed in the Binghamton area. IBM bailed out about 10 years ago, 15 years ago, and about 10,000 people lost their jobs. So one of our jobs in all of this is to rebuild a clean ecosystem with battery capabilities in the Binghamton area, and specifically in the Endicott facilities of IBM. And we now have a gigafactory just started up a few weeks ago with the first products coming out. And our prototype facility will be just down the street from them. So we're going all the way now from fundamental research to try to rebuild an industry in America. And I say America is going to be working with anybody who Washington thinks is friendly. And this includes the entirety of the American continent from the south to the full north, plus this little island continent to the west of America called Australia. They're considered part of North America, I think, for our battery supply chain. And I'll stop there, and I think we'll do the questions at the end of the session.